velocity of forced oscillator, okay. When a driving force periodic driving force when a periodic driving force F equal to F naught e to the power I omega t is applied to a damped oscillator and steady state is reached, the displacement is given by y displacement equal to I F naught upon omega Zm e to the power I omega t minus 5. Okay, when a periodic driving force F equal to F naught e to the power I omega t is applied to a damped oscillator and steady state is reached, the displacement is given by y equal to minus I F naught upon omega Zm e to the power I omega t minus 5, where Zm equal to under root of r square plus omega m minus s by omega whole square. That is equation number 1. And tan phi equal to omega m minus s by omega whole upon r. Okay, and r being the damping constant, m being the mass, and s the stiffness constant. Okay, then y equal to minus I F naught omega Zm in bracket e to the power I omega t minus phi is cos omega t minus phi plus I sin omega t minus phi. This is the equation number then y equal to minus I F naught upon omega Zm in bracket cos omega t minus phi plus F naught upon omega Zm sin omega t minus phi, okay, omega t minus phi, okay, omega t minus phi. Then this is the equation number 2. Okay, and put F equal to F naught e to the power I omega t in the form then F equal to F naught cos omega t plus I sin omega t. Okay, then F equal to F naught cos omega t plus I F naught sin omega t. This is the equation number 3. Okay, equation number 3. Comparing the equation number 2 with equation number 3, comparing the real part of equations second and third, we have when F equal to F naught cos omega t. This is the equation number 4. Okay, F equal to F naught cos omega t is equation number 4, and y equal to F naught by omega Zm sin omega t minus 5. This is the equation number 5. Similarly, comparing the imaginary part of equation second and third, we have similarly similarly comparing the imaginary parts parts of equation second and third of equation second and third. Okay, second and third. Okay, then f equal to f naught sine omega t and y equal to f naught by omega zm cos omega t minus phi. Okay, the velocity of a forced oscillator is defined as the rate of change of displacement with time. We shall calculate the value of velocity. Okay, the velocity of a forced oscillator, and the velocity of forced oscillator the velocity of a forced oscillator the velocity of forced oscillator defined as the rate of change of displacement with time. The rate of change of displacement with time. Okay, then the velocity of a forced oscillator. When a periodic driving force F equal to F naught e to the power I omega t is applied to a damped oscillator and a steady state is reached, the displacement is given by y equal to steady state reached when steady state reached y equal to minus I f naught upon omega zm e to the power I omega t minus phi. This is okay, and zm equal to under root of r square plus omega m minus s by omega whole square. This is equation number 1. Tan phi equal to omega m minus s by omega upon r. Okay, r being the damping constant, m being the mass, and s is the stiffness or spring constant. Okay, this is the equation number first, and equation number first can be put in the form. Then y equal to minus I f naught upon omega zm and e to the power I omega t minus phi. The value is cos omega t minus phi plus I sin omega t minus phi. Okay, then y equal to I f naught upon omega zm cos omega t minus phi plus f naught upon omega zm sin omega t minus phi. This is the equation number second, and f equal to, okay, this is the equation number second, and put f on this is the equation number second, and put f equal to f naught e to the power I omega t in the form. Then f equal to f naught cos omega t plus I sin omega t. Then f equal to f naught cos omega t plus I f naught sin omega t. Equation number third, comparing the real part of the equation number second and third. The real part equation number second is f naught upon omega zm sin omega t minus phi. Then f equal to f naught cos omega t. F equal to f naught cos omega t. F equal to f naught cos omega t. Equation number 4, and y equal to f naught upon omega zm sin omega t minus 5. Equation number 5. Okay, f equal to f naught cos omega t, f equal to f naught cos omega t, and y equal to f naught upon omega Zm sin omega t minus phi. Similarly, comparing imaginary parts of equation number second and third, f equal to f naught sin omega t, f equal to f naught sin omega t, and y equal to f naught upon omega Zm sin omega t minus phi. Okay, imaginary part y equal to f naught upon omega Zm cos omega t minus phi. The velocity of force oscillator is defined as the rate of change of displacement with time. We shall calculate velocity first point when the driving force is F. When the driving force is F naught cos omega t, and the second, when the driving force is f naught sin omega t, okay. Then first point, f naught sin omega t, then first point, okay. First point, driving force f naught cos omega t, driving force f naught cos omega t, okay. Driving force f naught cos omega t, okay. When the driving force is given by f equal to f naught cos omega t, the displacement of the force oscillator in the steady state is given by f equal to f naught cos omega t, okay. F equal to f naught cos omega t. The displacement of force oscillation is given by y equal to f naught upon omega Zm sin omega t minus phi, okay, at steady state, okay, in the steady state, okay. Then velocity v equal to dy by dt, that is f naught upon omega Zm and omega cos omega t minus phi, okay. Then omega is cancelled out by omega. Then velocity v equal to f naught upon Zm cos omega t minus phi equal to v naught cos omega t minus phi equal to v naught sin omega t minus phi plus pi by 2, okay. Where v naught equal to f naught upon Zm, okay. Then this is equation number ix9. This is equation number 9. This is equation number 9, and this is equation number v equal to dy by dt, f equal to omega, so omega cancel out, then v equal to f naught upon Zm cos omega t minus phi. This is v naught cos omega t minus phi. This is equation number 8. Equation number 8 equal to v naught sin omega t minus phi plus pi by 2 and where V naught equal to F naught upon Zm, equation number 9. Okay, comparing equation number 9 and 5, comparing equation number 9 and 5, 9 and 5, we find that the velocity always leads to displacement. We find that velocity velocity always leads the displacement by a phase angle pi by 2. Comparing equation number 8 with 4, and comparing equation number 8 with 4, compared with 4, we find that velocity lags behind that. We find that velocity lags behind the driving force, by a phase angle phi. Okay. Comparing equation number 9 and 5, we find that velocity always leads the displacement by a phase angle pi by 2. Comparing equation number 8 and 4, we find that velocity lags behind the driving force by phase angle phi. Okay. Second point, driving force F naught sine omega t. When the driving force F equal to F naught sine omega t, the displacement is given by y equal to F naught upon omega Zm cos omega t minus phi. Then velocity equal to dy by dt, that is minus F naught upon omega Zm minus omega sine omega t minus phi. Okay, equal to F naught upon Zm sine omega t minus phi equal to V naught sine omega t minus phi equal to V naught cos omega t minus phi plus pi by 2, where V naught equal to F naught upon Zm. Okay, V naught equal to F naught upon Zm. Comparing equation number 11 and 7, comparing equation number 11 with 7. Okay, this is the equation number 11, and this is equation number 10. Okay, comparing equation number 11 with 7, we again find that velocity always leads the displacement by of phase by a phase angle pi by 2, by a phase angle pi by 2. Okay, comparing equation number 10 and 6, comparing equation number 10 and 6, comparing equation number 10 with 6. Okay, we again find that velocity lags behind the driving force by a phase angle phi, Okay, it's okay, good, thank you. Next, studying variation of velocity amplitude with driving force frequency. Okay, variation of velocity amplitude with driving force frequency. Okay, we have seen in the above discussion that when the applied force F equal to F naught cos omega t, applied force F equal to F naught cos omega t, the velocity force vibration is V equal to V naught cos omega t minus phi, and when the applied force F equal to F naught sin omega t, the velocity of force vibration is V equal to V naught sin omega t minus phi. Okay, where V naught equal to F naught upon Zm, and the amplitude of the velocity in each case, V naught equal to F naught by Zm, that is F naught by under root of R square plus Xm square, that is F naught upon under root of R square plus omega m minus s by omega whole square. Okay, this is the equation number X12. Okay, on the previous X1, X2, X3 previous heading. Okay, X12, and we shall discuss the behavior of velocity, amplitude versus driving force frequency in three stages: low frequency, high frequency, and resonant frequency. Okay, first point, low frequency. Okay, according to equation number 12, according to equation number 12, the mechanical impedance Zm equal to under root of R square plus omega m minus s by omega whole square. Okay, where omega m minus s by omega equal to Xm is known as mechanical reactance. It is consist of two parts, omega m and s by omega, for low frequency. S by omega is a large quantity. larger quantity. Okay, large quantity. In such a case, the impedance Z depends upon S and is said to be stiffness controlled. Okay, large quantity. Okay, in such a case, in such a case, in such a case, in such a case, the impedance, in such a case, the impedance Zm depends upon depends upon S and said to be or stiffness controlled. Stiffness 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 controlled. Okay, when omega is tends to 0, then m omega is tends to 0, and s by omega is tends to infinite, then Zm equal to r square plus s square by omega square whole to the power 1 by 2 equal to s by omega. As s by omega is very large quantity and r square can be neglected as compared to s square by omega square. Okay, as s by omega is very large, very large quantity, and r square can be neglected as compared to s square by omega square. Then b naught equal to f naught by Zm equal to f naught by s by omega, that is f naught omega by s. Okay, when omega is tends to 0, then v naught is tends to 0. Okay, v naught is tends to 0 because Zm equal to r square plus omega m minus s by omega whole square. Okay, Zm equal to under root of r square plus omega m minus s by omega whole square. Okay, and b naught equal to f naught upon under root of r square plus omega minus by omega square. Then as a low frequency, according to equation number 12, the mechanical impedance Zm equal to under root of r square plus omega m minus s by omega whole square. Okay, then where omega m by s by omega equal to maximum mechanical reactance for low frequency s by omega is a large quantity. In such a case, the impedance Zm depends upon the s and said to be stiffness controlled. When omega is tends to 0, then m omega is tends to 0 and s by omega is infinite, and Zm equal to under root of r square plus s by omega whole square whole to the power 1 by 2 equal to s by omega. Okay, s by omega. As s by omega is a very large quantity and r square can be neglected as compared to s square by omega square, then v naught equal to f naught upon Zm. Zm equal to f naught upon s by omega equal to f naught omega by s. Okay, f naught omega by s. When omega equal to 0, then v naught equal to 0. Omega equal to 0, and V naught equal to 0 because the value of S is very high. Okay? Okay? Then S by omega equal to infinite, and omega by S equal to 0. Okay? Then V naught equal to 0. Okay? At a high frequency, second point. Second point is a high frequency. High frequency. Okay? High frequency. At a high frequency, omega m is a large quantity. Omega m is a large quantity. At high frequency, at high frequency, omega m is a large quantity. Large quantity. Omega m is a large quantity. Okay? If omega m is a large quantity, then in such a case the impedance Zm depends upon m and is said to be mass controlled or inertia controlled. Okay? In such a case, the impedance Zm depends upon m and is said to be mass controlled or inertia controlled. Okay? Are said to be inertia controlled when omega tends to infinite, then m omega tends to infinite, but s by omega tends to 0. Okay? Then Zm equal to Zm equal to in bracket r square plus m omega minus s by omega whole square all to the power 1 by 2 equal to in bracket r square plus m square omega square all to the power 1 by 2 equal to m omega. Okay? Because m omega is very large, m omega is very large, then r square can be neglected. R square can be neglected as compared to m square omega square. Then V naught equal to F naught upon Zm. V naught equal to F naught upon Zm. That is F naught upon m omega, where omega tends to infinite, then V naught tends to 0. Okay? Next, at a resonant frequency. Okay? At a resonant frequency. Third point, resonant frequency. Okay? At a resonant frequency. For a frequency omega naught, at which omega naught m equal to s by omega naught. Okay? For a resonant frequency, omega naught at which omega naught m equal to s by omega naught, the reactance xm equal to omega naught m minus s by omega naught equal to 0, and Zm has its minimum value given by Zm equal to R. Zm equal to R, it is a real quantity with zero reactance. It is a real quantity is real quantity. It is a real quantity, okay? It is a real quantity, okay? With a zero reactance. Reactance, okay? At this frequency, the velocity increases at maximum value. At this frequency, the velocity amplitude has its maximum value V naught equal to F naught upon Zm equal to F naught by R. This frequency omega naught is known as frequency of velocity resonance. This frequency omega naught is known as the frequency of velocity resonance, okay? Thus, at frequency of velocity resonance, the velocity amplitude depends upon the driving force F naught and R, resisting force per unit velocity, but is independent on frequency. Velocity resonance occurs at natural frequency of oscillators, okay? Velocity resonance occurs at natural frequency, okay? For velocity resonance, omega equal to omega naught equal to under root of S by M, natural frequency of the oscillator. This can be proved as follows. Natural frequency of the oscillator, natural frequency of the oscillator, okay? V naught equal to F naught by Zm. V naught has maximum value and Zm is a minimum. Now Zm is minimum for frequency given by dZm upon d omega equal to 0, okay? V naught equal to F naught by Zm, comma, V naught has minimum when Zm is minimum, okay? Minimum. Now Z is minimum. Now Zm is minimum for a frequency given by dZm upon d omega equal to 0, okay? As Zm equal to in bracket R square plus omega m minus S by omega whole square whole to the power 1 by 2, okay? Then dZm upon d omega equal to 1 by 2 in bracket R square plus omega m minus S by omega whole square whole to the power minus 1 by 2 into 2 omega m minus s by omega m plus s by omega square whole equal to 0. Then omega m minus s by omega plus m plus s by omega square equal to 1 by omega in bracket omega minus omega m minus s by omega and omega m plus s by omega equal to 0. Okay, and omega square m square minus s square by omega square equal to 0. Then omega to the power 4 equal to s square by m square and omega equal to under root of s by m equal to omega naught. Okay, this is the we will be plotting the graph between omega and velocity. This is v velocity and this is midpoint omega naught, and the first graph is starting from here and going up to the top, and after top and downwards to x-axis, and this is the second graph plotting. Okay, this is the first graph and this is the second graph, and this is a figure A, and in figure B this is plus pi by 2 and this is omega, this is 0 and phi, this is minus pi by 2 this is omega naught, okay, omega naught. Okay, the variation of magnitude of velocity with frequency of a driving force is shown in this figure A. At a resonance frequency B not equal to f naught by r, resonance frequency B not equal to f naught by r, the height and sharpness of the peak at resonance depends upon r. For a small value of r, the velocity at resonance is very large curve first here, and for large value of r, the velocity has been a smaller value curve second. Okay, and the flat curve is that a flat curve. Okay, next, variation of phase difference between velocity and driving force frequency. Okay, variation of phase difference between velocity and driving force frequency. Okay, the velocity for force oscillator is given by v equal to f naught upon zm cos omega t minus 5. Okay, when the driving force is given by f equal to f naught cos omega t. Okay, the phase difference between velocity and driving force is minus 5. The phase difference between velocity and driving force is minus 5. Okay, is that the velocity lags behind the driving force, lags behind the driving force. driving force by an angle phi is given by tan phi equal to omega m minus s by omega whole upon r. Okay, first point. Okay, first point, low frequency. At a low frequency, omega tends to approx 0. Okay, omega 0, then m omega is 0 and s by omega is infinite. Okay, then tan phi equal to infinite minus infinite and phi equal to minus pi by 2. Okay, phase difference between velocity and driving force. Phase difference between velocity and driving force minus pi equal to plus pi by 2, hence the resulting velocity leads the driving force by phase angle pi by 2. Okay, second point, high frequency. Okay, at high frequency, omega tends to infinite, then m omega tends to infinite and s by omega tends to 0. Then tan phi equal to plus infinite and phi equal to plus pi by 2. Phase difference between velocity and driving force. Then a phase difference between velocity and driving force and driving force equal to minus phi by 2, hence the resulting velocity lags behind the driving force by phase angle pi by 2. Third point, resonance frequency. Okay, at resonance frequency, omega equal to omega naught equal to under root of s by m, or omega square equal to s by m, or m omega equal to s by omega. Then tan phi equal to 0 or phi equal to 0. The phase difference between velocity and driving force. The phase difference between the phase difference between driving force, between velocity and driving force and driving force driving force minus phi equal to 0, hence resulting velocity is in phase with the driving force, okay. Hence, as the driving force frequency increases from 0 to omega naught and velocity lags behind the force by an angle pi by 2. Hence, as the driving force frequency increases from 0 to omega naught, the velocity lags behind. The velocity lags behind the force by an angle pi by 2, which slowly increases to 0, which slowly increases to 0 when the velocity is in phase with the force, okay. And further increasing the velocity, the velocity leads the force, and as omega approaches infinite, the angle of leads approaches pi by 2, okay. Yes, thanks. Phase difference at a displacement, resonance and velocity resonance, okay. Phase difference at displacement, resonance and velocity. Phase difference at displacement, resonance and velocity resonance. Phase difference at displacement, resonance and velocity resonance, okay. When a period force F equal to F naught cos omega t, this is the equation number first, is applied to a damped oscillator and steady state is reached, the displacement is given by y equal to F naught upon omega Zm sin omega t minus phi, okay. At a steady state is reached, okay. The displacement is given by y equal to F naught upon omega Zm sin omega t minus phi. This is the equation number second. Okay. Where Zm equal to under root of r square plus omega m minus s by omega whole square, okay. R is the damping constant, m is the mass, and s is the stiffness, spring constant, okay. The phase difference between driving force and displacement of force oscillator is given by the phase difference between the driving force and displacement of force oscillator of a forced oscillator is given by tan phi equal to omega m minus s by omega by r. Okay, this is the from equation number second can be put in the form, and from equation number second can be put in the form y equal to f naught upon omega zm cos omega t minus phi plus pi by 2. Okay. Okay. Then comparing equation number first and third, this is equation number third. Okay, and comparing equation number first and third, equation number first and third. Okay, we find the displacement lags behind the driving force by an angle. The displacement, we find that the displacement lags behind the driving force. Displacement lags behind the driving force. Driving force by an angle phi plus pi by 2 at displacement resonance omega m equal to s by omega r omega m minus s by omega equal to 0. Okay, displacement resonance. Okay, then tan phi equal to 0 or phi is equal to 0 at resonance displacement. Show at resonance displacement lags behind the driving force, lags behind the driving force by an angle pi by 2. Okay, for the same period force for the same period force F equal to F naught cos omega t. The velocity of the force oscillator is given by V equal to F naught upon Zm cos omega t minus phi. Okay, and phase difference tan phi equal to omega m minus s by omega upon r. Okay, at velocity resonance again, omega m equal to s by omega r, omega m minus s by omega equal to 0, then tan phi equal to 0 or phi equal to 0. Okay, at resonance velocity, at resonance velocity is in phase with the driving force, phase with the driving force, okay, with the driving force, okay. Then phase difference at displacement resonance and velocity resonance. Displacement resonance and velocity resonance. If for driving force F equal to F naught cos omega t, and at steady state condition, reduce y equal to F naught upon omega Zm sin omega t minus phi. This is equation number second, where Zm is the under root of r square plus omega m minus s by omega whole square. The phase difference between the driving force and displacement of force oscillator is given by tan phi equal to omega m minus s by omega by r. Okay? From the equation number second, y equal to f naught by omega Zm and cos omega t minus phi plus pi by 2 minus phi plus pi by 2. Equation number third. Comparing first and third, we find the displacement lags behind the driving force by an angle phi plus pi by 2. Okay? Displacement lags behind the driving force by an angle phi plus pi by 2. Okay? Then at a displacement resonance omega m equal to s by omega r omega m minus s by omega equal to 0. Tan phi equal to 0, then phi equal to 0. At resonance displacement lags behind the driving force by an angle pi by 2. Okay? For the same period, force F equal to F naught cos omega t B equal to F naught by Zm cos omega t minus phi, and phase difference tan phi equal to omega m minus s by omega by r. At velocity resonance against omega m equal to s by omega, or omega m minus s by omega equal to 0. Then tan phi equal to 0, or phi equal to 0. At a resonance velocity is in phase with the driving force. Velocity is phase with the driving force at the resonance conditions. Okay. Displaced resonance occurs at slightly less frequency than velocity resonance. Okay. When the driving force is given by, when the velocity resonance occurs at a frequency, the velocity resonance occurs at a frequency when omega equal to omega naught, where omega naught is the frequency of free oscillation. Omega naught is the frequency omega naught is frequency of free oscillation. Omega naught equal to frequency of free oscillations of the forced oscillator, forced oscillator. Okay, forced oscillator. Okay, and the displacement resonance takes place at a frequency, and the displacement resonance takes place at a frequency omega dash equal to omega naught under root of 1 minus r square upon 2 m square omega naught square. Okay, since r, m and omega naught are all the positive quantity being squares, the displacement resonance occurs at a frequency omega dash slightly less than omega, the frequency of velocity resonance. Frequency of velocity, resonance. The displacement resonance takes place at a frequency omega dash equal to omega naught and root of 1 minus r square upon 2 m square omega naught square. And since Rm and omega naught, since Rm and omega naught is positive, the displacement resonance occurs at the displacement resonance occurs at a frequency omega dash slightly less than omega, the frequency of velocity resonance, okay.